Today we are going to learn about sources of energy: hydropower, biogas, nuclear reactors. Hydroelectric power.
Hydroelectric power is generated using the force of falling water. Water is held behind a dam, forming an artificial lake or reservoir. When electricity is needed, some of the water in the reservoir is released through a water intake in the dam. Gravity causes the water to fall through a pipe inside the dam called a penstock. The falling water spins a turbine, a type of water wheel that converts the water's energy into mechanical power, which is located at the end of the penstock. When the turbine spins, it turns a metal shaft which goes up to an electrical generator. As the shaft turns, it causes the generator to rotate, producing electricity. After flowing through the penstock and across the turbine, the water continues into the river on the other side of the dam. Hydroelectric power is a renewable source of energy. It's also one of the most cost-reliable forms of electric production.
Biogas.
Working of biogas plant. The maize from the tractor is collected in a storage bin. The storage bin is fitted with a hydraulic belt which continuously feed the maize to the conveyor belt. The liquid manure, important substrate, is mixed with the maize in the blending pump. The pump is fixed with rollers. In this way, the maize is blended with liquid manure before fermentation in fermentation tank. Now, the liquid waste is heated with hot water at 70 degrees Celsius in a tubular heat exchanger using a counter current process. After heating for 1 hour, the hydrogenation of substrate is complete, and now they can be poured into the fermenters or fermentation tank. The substrate here is continuously stirred in order to prevent formation of layers of material. Then a hot water boil heater boils the substrate at about 35 degrees Celsius to 55 degrees Celsius. In order to accelerate the formation of methane on average, substrate is in the fermenter for about 30 days before it is filled in another fermenter for a further 30 days to complete the gas formation process. During this time, slurry undergoes fermentation in the presence of anaerobic bacteria with a gradual evolution of biogas, which starts collecting in the dome-shaped space. As the time passes, more and more biogas is collected inside the dome, thereby exerting pressure on the slurry in the tank, and this in turn forces the slurry to overflow. This slurry, withdrawn periodically, is used as a manure. When fermentation is completed, the thin liquid substrate is pumped into two reinforced concrete tanks where it is stored until it can be brought out in the fields.
Nuclear energy.
We use electricity to power every aspect of our lives. Simple stuff like making a cup of tea or powering our tablets and phones. We are on a journey to find out where some of this electricity comes from. We're inside a nuclear reactor, and if you look below you, you'll see we're travelling downwards, towards the reactor core. This system has just been refueled. It is powered by fuel rods that contain uranium, which is a natural element that is mined from deep in the ground. We keep it here, inside these metal rods. Let's take a look inside. The system is about to be switched back on. To see how uranium makes energy, we'll need to get smaller though. Now we're shrinking to an atomic level. Here, right in front of you, there's rows and rows of uranium pellets. In total, there are over 2 million fuel pellets in the whole reactor. And it's inside these pellets, each only a centimetre tall, that nuclear fission happens. Let's get even closer. At this scale, we can see actual atoms and neutrons. Neutrons are the particles that help us unlock all that energy from the nucleus. But they move fast, so first we need to slow one down. And to do that, we simply use water. Let's follow this one and see where it leads us. Pay close attention. Firing this neutron into the nucleus of the atom causes the nucleus to split in two. This is the fission we mentioned earlier. And as the nucleus splits, it releases its own neutrons. Some of these newly released neutrons, slowed by the water, hit other atoms, causing more fission. And so the chain reaction begins. In our reactor, there are an incredible 5 million fissions per pellet per second. Look around you, and you'll see them happening everywhere. Each time a uranium nucleus splits, it releases its awesome energy. This energy heats the fuel pellets, and in turn the water in the reactor, to more than 300 degrees Celsius. The powerful chain reaction has heated the water in the reactor core, and this heated high-pressure water now travels through pipes out of the reactor vessel at 35 miles per hour. It all sounds very dramatic, but understanding the physics means we know how to regulate the chain reaction. In the space beyond the pipe, the heat from that water turns more water into steam. This steam is what drives the turbines. All of that power just to make a turbine spin. It's really quite a simple system. These steam-driven turbines generate more than 1,000 megawatts of electricity. That's roughly enough to power all of the houses in Greater Manchester. All of the steam leaving the turbine is condensed back into water and pumped back round to the steam generators to be turned back into steam again. So, here we are, back in the main reactor where we started. You see, the simplicity of this system makes nuclear power incredibly effective. As you've seen, with nuclear, a little goes a very long way. Something to think about when you next make a cup of tea or charge your tablet.
Now, we are going to see comparison between atom bomb and hydrogen bombs. Now we are going to learn about solar energy. Solar energy.
The Earth intercepts a lot of solar power, 173,000 terawatts. That's 10,000 times more power than the planet's population uses. So is it possible that one day the world could be completely reliant on solar energy? To answer that question, we first need to examine how solar panels convert solar energy to electrical energy. Solar panels are made up of smaller units called solar cells. The most common solar cells are made from silicon, a semiconductor that is the second most abundant element on Earth. In a solar cell, crystalline silicon is sandwiched between conductive layers. Each silicon atom is connected to its neighbors by 4 strong bonds, which keep the electrons in place so no current can flow. Here's the key. A silicon solar cell uses 2 different layers of silicon. An N-type silicon has extra electrons, and P-type silicon has extra spaces for electrons, called holes. Where the 2 types of silicon meet, electrons can wander across the p-n junction, leaving a positive charge on one side and creating negative charge on the other. You can think of light as the flow of tiny particles called photons shooting out from the sun. When one of these photons strikes the silicon cell with enough energy, it can knock an electron from its bond, leaving a hole. The negatively charged electron and location of the positively charged hole are now free to move around. But because of the electric field at the p-n junction, they'll only go one way. The electron is drawn to the n side, while the hole is drawn to the p side. The mobile electrons are collected by thin metal fingers at the top of the cell. From there, they flow through an external circuit, doing electrical work like powering a light bulb, before returning through the conductive aluminum sheet on the back. Each silicon cell only puts out half a volt, but you can string them together in modules to get more power. 12 photovoltaic cells are enough to charge a cell phone, while it takes many modules to power an entire house. Electrons are the only moving parts in a solar cell, and they all go back where they came from. There's nothing to get worn out or used up, so solar cells can last for decades. So what's stopping us from being completely reliant on solar power? There are political factors at play, not to mention businesses that lobby to maintain the status quo. But for now, let's focus on the physical and logistical challenges. And the most obvious of those is that solar energy is unevenly distributed across the planet. Some areas are sunnier than others. It's also inconsistent. Less solar energy is available on cloudy days or at night. So a total reliance would require efficient ways to get electricity from sunny spots to cloudy ones, and effective storage of energy. The efficiency of the cell itself is a challenge too. If sunlight is reflected instead of absorbed, or if dislodged electrons fall back into a hole before going through the circuit, that photon's energy is lost. The most efficient solar cell yet still only converts 46% of the available sunlight to electricity, and most commercial systems are currently 15 to 20% efficient. In spite of these limitations, it actually would be possible to power the entire world with today's solar technology. We'd need the funding to build the infrastructure and a good deal of space. Estimates range from tens to hundreds of thousands of square miles. Which seems like a lot, but the Sahara Desert alone is over 3 million square miles in area. Meanwhile, solar cells are getting better, cheaper, and are competing with electricity from the grid. And innovations like floating solar farms may change the landscape entirely. Thought experiments aside, there's the fact that over 1 billion people don't have access to a reliable electric grid, especially in developing countries, many of which are sunny. So in places like that, solar energy is already much cheaper and safer than available alternatives like kerosene. For, say, Finland or Seattle, though, effective solar energy may still be a little way off.
Thank you for your support.